Hello, let me begin with an incident. Back in 2021, April 28th, during the pandemics, at around 2 p.m., we felt major tremors in our locality, followed by back-to-back tremors. We realized that a major earthquake has hit our region. We also realized that we were very much underprepared to respond to such phenomena. Even though no loss of human life was reported, major damages to infrastructure occurred. And more importantly, it also exposed the underpreparedness of the disaster management agencies and netizens alike to respond to such phenomena. The goal of my presentation is to formulate a reliable model to forecast earthquake in the northeastern region of the Indian plate. My name is Mintu Kumar Chetri. I am a student of LJMU MSc DS Cohort 10. The title of my study is Forecasting the Magnitude of Earthquake in the Northeastern Region on the Indian Plate under the supervision of Probin D. Chogale. The agenda of the study revolves around the following headings: motivation, which I have touched upon briefly, then the related research work that has gone through in forecasting such natural disasters, and more precisely the earthquake, aims and objective, research methodology that will be deployed, and actual implementation, the results of that implementation, conclusion, followed by recommendations. Now we realize that the motivation is the target region itself, which is a high seismic zone, as evident from figure 1.1. More than 4,000 earthquakes have occurred in this region since 1975. Large earthquakes in the range of 8.3 and 8.6 have occurred in 1897 and 1950 respectively. More than 5,000 human life was lost. Hence, a good forecasting model would help design framework for proactive preventive readiness. More than 124 papers were scanned from the various time period to understand the related works carried out in the field of natural disaster and particularly earthquake. In this presentation, we will discuss few of them. First, a fuzzy expert system for earthquake prediction uses the adaptive network-based fuzzy inference system and FIS model to predict earthquake. This model uses the refined version of the legacy FES system. The results of the train expert system are encouraging over the earthquake magnitude greater than 5.5, but relatively higher number of false alarms are generated for earthquake magnitude greater than 6. In the second study, autoregressive moving average ARMA model was used. ARMA model with P is equal to 5 and Q is equal to 5 can predict 10 occurrences for the next 6 years as per the model. In the third study, LSTM model was used. LSTM model highlights the superiority over the regular feed-forward neural networks. The score of the test data is 59% higher than the normal feed-forward neural network. Similarly, other models like deep learning and classifications were used in the other studies. Further, parallel vector regression, DNN and clustering, multifractal detrended fluctuation analysis MFDFA, etc. were also used. We can conclude that the earthquake prediction has developed into an emergent discipline. Accompanied by big data analytics, accurate forecasting capabilities can be generated, which can provide valuable insights to stakeholders. But those research do have some gaps. We try to highlight some gaps. In the existing studies, even the most advanced techniques are facing difficulties while dealing with earthquake prediction. Second, variation in the frequency of earthquake is not addressed, which may have led to stress buildup in the convergence zone. Another question remains relatively unanswered. That is, do earthquake occurrence and magnitude follow a pattern? Fourth, based on visualization and interpretability of the output to the observers and the stakeholders per se, which are the best performing models? This question also remains unanswered. Now, based on the motivation, the related study, and the research gaps, the aims and objective of the study can be formulated, which should enable the evaluation of the various work of research carried out by other academics in predicting earthquake across the globe and its significance. Also to explore and deploy time series forecasting and machine learning models for earthquake prediction. And to identify the best tuned models by use of model evaluation techniques and relevant optimization. And finally, to add to the vast existing knowledge of ML models for forecasting earthquake. Just like any other data science problem, we use the following steps to achieve the desired result. That is covered in this section called research methodology. Data collection from the real world, understanding of the same data with respect to its columns, variables, and also interpretation to some extent. Then importing the required libraries to interpret the data as well as to understand the data further, the data type. And data preparation and transforming the data for further analysis. Then exploratory data analysis to understand the various facets of the data, the various properties of the data. Then finally curate the data for model building. And then explore various models, which is explained in figure 1.2, where it starts in the basic model, then it goes to the autoregressive model, and then also deploys the RME model, which is followed by the evaluation, optimization, and comparison. The implementation section actualizes the methodologies identified in the earlier section. It starts with data preparation. All other variables are eliminated except depth, magnitude, and time. Data conversion, like the time variable, is converted to date time format. The column time is renamed as month and indexed accordingly. Data is also aggregated, like occurrence per month as oc_mag, maximum magnitude per month as max_mag, and average depth of occurrence per month as average_mag. EDA helps us to explore the data. This is done by plotting. The time series plot is done to check whether there is any variation in the plot. Histogram and box plot is done to check the spread of the data and to check outliers. Accordingly, to treat the missing values if there are any missing values. Time series decomposition is done to understand the various properties of the time series, like level, trend, seasonality, or noise. And finally, the data is split into training set and test set. With the earlier steps, the data is now ready for the basic forecast model. In the basic forecast model, naive method, simple average method, simple moving average method, simple exponential smoothing method, halt exponential smoothing method, and halt Winters multiplicative method were implemented. However, there are some prerequisite arrangements for autoregressive forecast models, like the time series data should be stationary, means the variance and covariance and the label should be same. The stationarity test helps us to understand whether the trend is stationary or not. KPSS and ADF tests helps us to identify whether the dataset is stationary or not. If the data is non-stationary, then transforming and differencing is done to attain stationarity. Further, ACF and PACF helps us to understand the autocorrelation function, which are important parameters for autoregressive forecast models. PACF gives us the p-value, ACF gives us the q-value. Models like autoregressive MA, autoregressive moving average, autoregressive integrated moving average, and seasonal autoregressive integrated moving average are used. Figure 1.5 shows a SARIMA model against the variable oct_mag. Figure 1.6 shows a LSTM model under variable max_mag for the LSTM method. The results section helps us compare the optimized output of all the relevant models. In this case, the LSTM model with look back equal to 10, epoch equal to 100, batch size equal to 128 performs better with respect to variable oct_mag. Similarly, with respect to variable max_mag, LSTM with look back equal to 15, epoch equal to 100, and batch size equal to 128 performs the best with a RMSE score of 0.13 and a MAVE score of 2.2. Hence, we can conclude that the LSTM model has superior forecasting capabilities in both evaluation criteria and variable. In the results section 2, we check the performance of the model with respect to visualization and interpretability to observers. Figure 1.7 shows a SARIMA model with slightly deviated RMSE and MAVE, but the forecast trend is in line with the test data. The corresponding RMSE and MAVE score is highlighted in table 1.3. With respect to visualization and interpretability too, the LSTM model has superior forecasting capabilities in both evaluation criteria and visualization. This section covers the summary of the insights. It is observed that the frequency of the earthquake occurrence is noticeably increasing in the research area month on month, which is a cause of concern. The trend of maximum magnitude is slightly increasing, but the mean is approximately 5. The model could not capture the gap between large earthquakes and predict the occasional peak. Hence, there is a clear opportunity of future research and studies combining both frequency and magnitude data over ensemble techniques. SARIMA with particular input parameters and LSTM with optimized parameters are better models to forecast earthquake. Outcomes clearly suggest that the LSTM model can be deployed in the real world. Combination of both visualization and evaluation metrics is advocated for better interpretability to observers. Recommendations. The research was carried out with limited data. However, with additional consideration of precursors, more historical data and correlated features should provide better insights and better forecasting capabilities of model. Data from other sources could authenticate the assumption of single source of truth principle. The forecasting can be narrowed to days rather than months with latest sophisticated earthquake measurement tools and improved data quality and storage. Even real-time information and alerts can be achieved if advanced AI techniques, live feed, satellite imaging, and social media inputs can be used. Also, an ensemble of all these techniques along with the LSTM model, which is the best model in our case, can be used to have better precision. References. Thank you. Thanks for the time.